Hello everyone, in this video I am planning to share an overview about microstrip antennas, which is also known as the patch antennas. So let's see some basics of the microstrip antenna. So if you consider a microstrip antenna, you can see that it will be having a radiating patch which is supported by a dielectric and a ground plane. So this is the basic structure of the microstrip antennas, and we will be having the feed and the signal will be fed through this feed antennas. So when the signal is fed, you can see that these two slots. So here you can see that these two edges along the feed line will be forming the radiating slots. So the radiation will be happening along these slots. They are known as the radiating slots. The shape of this radiating patch can be of different types like rectangular, circular, or different types of meandering structures. These can be based on our requirements like which are the frequency requirement, radiation pattern requirement, polarization requirement. So based on that, we can choose different types of geometries. So let's see what are the main advantages of microstrip antennas. So when you consider the um, microstrip patch antenna, you can see that it is consisting of a radiating patch which is backed by a grounded dielectric. So we have seen that in earlier days it is mostly the wire antennas, and you have seen the mobile phones occupied with wire antennas and these type of antenna structures, right? But due to the introduction of the microstrip patch antennas and due to their low profile characteristics, nowadays we can have the smaller mobile phones. So one of the advantage of the patch antenna is low profile. That is, this the thickness is very small and we will be having lesser size. Another one is these structures are conformal. If you have the flexible dielectric, you can make the conformal antennas and it can be uh, pasted onto different type of conformal structures. And another one is it is easy to manufacture because we know that it is based on the PCB technology, so it is very easy to manufacture with more precisions. Another one is it is very easy to make modification on resonant frequency, polarization, pattern, and impedance. That is by changing the shape and the size of these patterns, it is very easy to make the modification on the parameters. So let's see some of the disadvantages of patch antennas. So the first one is low efficiency. We know that the patch antennas are backed by the dielectric. So this dielectric will be having some losses. Due to these losses in the dielectric, some of the energy will be lost in this dielectric and the efficiency, that is the power which is getting radiated, will be very less. That is why it will be having lower efficiency. Another disadvantage is high Q. In our previous video, we have explained what is meant by Q factor of the antenna. So based on that definition, Q factor is defined as 2 pi into energy stored by energy dissipated. So if you consider this antenna, you can see that this radiating patch is made up of the metal, ground is also made up of the metal, and there is a dielectric in between them. So we can consider this as a capacitor. So as it is like a capacitor, the energy stored inside this capacitor will be very high as compared to energy dissipated. So it will be having high Q. Because of this high Q of the antenna, the bandwidth of the operations will be very less. Another disadvantage is when you consider these, sorry, 1 minute. Okay. So when you consider the antenna feed, here you can see that some of the radiations is going out of the feed line. So this will cause disturbance in the network if there is any other antennas or any other things are connected to this. So because of this spurious radiation, it can cause the interference. And because of these type of radiation fringing effect, it can also cause the surface waves. So these are some of the disadvantages of the antenna. So let's see some of the parameter consideration for the microstrip antennas. So the thickness of the substrate has to be within this range, that is, it has to be within 0.003 lambda 0 to 0.05 lambda 0, where lambda 0 is the free space wavelength. So this is some of the factors. So if we are using the higher substrate thickness, so this is the case for a lower substrate thickness, and this is the case for the higher substrate thickness. So we have seen that it can be considered as a capacitor because this is the metal which is separated from the ground plane by the dielectric. So in effect, this is forming a capacitor. So it is like the capacitor, and when the thickness of the capacitor increases, that is, when the dielectric thickness increases, the thickness of the capacitor will increase, and this increase in the thickness will cause the reduction in the capacitance of the structure. So if there is the reduction in the capacitance, the Q factor of the antenna will decrease, and it will cause the increase in the bandwidth. Or in other words, we can say that if the thickness increases, the fringing field or the radiation will be more. So because of that, the bandwidth can be increased. So one of the solution, if you are looking for the larger bandwidth, is increase the substrate thickness. But it also has some disadvantages. It can cause the surface wave problem. So it is very essential to make sure that the thickness of substrate is within the specified range so that it will not cause any surface wave problems. Another parameter of the dielectric is permittivity of the substrate, and we usually prefer the range from 2.2 to 12. So if you are going to use the higher dielectric constant, you can produce very smaller element sizes. And if you are going to use higher values, it will cause less efficiency because we know that there will be some dielectric losses happening inside the dielectric, and it can cause the less efficiency, and it will be having the smaller bandwidth. So it is very essential to consider the permittivity and thickness of the substrate while designing your antennas. So in most of the MMIC designs, it is preferable to have thin substrate with high dielectric constant. So if we are going to have the thin substrate and high dielectric constant, it can tightly bound the fields within this dielectric, and there won't be any spurious radiation as we have seen in these type of structures. So it can effectively reduce the interference in a PCB structures. That is why this is one of the requirement if we are going to have the antenna getting designed. Okay. So next we can see some basics about the rectangular patch antenna. So if we consider the rectangular patch antenna, it will be having the length approximately equal to half the wavelength, and it will be having a thickness of the H. This dielectric thickness is H, and this is the width dimension, and this is the feeding point of the rectangular patch antenna. So for our further analysis, let's consider this microstrip rectangular patch antenna having dimension length L and width W, which is supported by a grounded dielectric having the permittivity epsilon R. So along the L is the radiating slots. So when it is fed along this direction, the radiations will be happening across these opening slots. So these are the radiating slots. As the dimension of the length and width are finite, this some of the radiations will be extending through the air. So this is known as fringing. So in ideal case, all of the field has to be confined within these boundaries like the patch, dielectric and the ground. So it has to be confined within that boundary. But as the dimension of the length and width is very finite, some field will be extend through the air. So this is known as the fringing field. So the fringing effect actually depends upon the dimension of the patch, that is length and width. So here I have shown only the fringing along the length, which depends upon the width. So fringing can also happen along this dimension also. So fringing will be happening across the opening slots. So the amount of fringing actually depends upon the dimension of the patch, the dielectric material of the dielectric material of the antenna. So next, let's see what is meant by effective permittivity. So we have seen that what is meant by fringing, and if you cut along this plane, this will be the side view of the plane. So this is the length of the patch, and here you can see that the variation of the field inside the dielectric. Here you can see that this is like a half wave variation. So the field is at this end, the field is going from the ground to the patch, and at this end it is coming from the patch to the ground plane. So here you can see that at these ends the fields are actually going inside the dielectric and through the air. So in effect it is actually transmitting through the uh, propagating through the dielectric and the air. So because of that we can consider this structure like this. So it will be having the dielectric and the air. So a combination of both this dielectric and the air will constitute the effective permittivity, which can be given by epsilon r effective equal to epsilon r, which is due to this dielectric, and plus 1. So which is the relative permittivity of the air, that is 1 epsilon r plus 1 by 2 plus epsilon r minus 1 by 2 into 1 plus 12 h by w, because we are considering the fringing along these dimension, which is the w, that is why this factor has come whole to the power of minus 1 by 2. So this is the effective permittivity of the material. So while designing the antenna, because we know that the length of the antenna is approximately equal to half the wavelength. So when you consider the wavelength, you have to consider this epsilon r, because it is like guided inside the dielectric and guided inside the air. So while designing the length, you have to consider the effective permittivity. Next, let's see what is meant by the effective length. So we have seen that there is fringing along these radiating slots. Due to this fringing, the effective length of the antenna will get increased. So here you can see that as the radiation is happening through this area, this length also has to be considered while considering the antenna as a whole. So in effect, we are designing only this much, or we are fabricating only this much, but in actual scenario, this much length is contributing for the radiation. So that is what it is shown here. Even if we are fabricating this much length, due to the fringing effect, it will be get extended to delta L along both the directions. So that delta L is calculated based on this equation, which can be given by the expression 0.412 h epsilon r plus zero point 0.3 into W by H plus 0.264, uh, these whole things. So if we have to design the patch antenna, we have to only calculate L. So the total effective length, so this is the total effective length, which is corresponding to lambda g by 2. So here effective length is given by lambda g by 2. So lambda g is equal to c by 2, c by fr into root of epsilon effective and into 2. So this lambda g by 2. So this is how the effective length is happening. So if you are designing the antenna, L can be calculated by L effective minus 2 delta L. So that is the importance of effective length of the antenna. Another important parameter is width of the patch antenna. Width of the patch antenna can be given by the expression lambda g by 2, where lambda g is given by c by fr into square root of 2 by epsilon r plus 1. So this will corresponds to the lambda g along the width and divided by 2. So that is the dimension of the width. So next important parameter is input impedance of the antenna. You have seen that when you are designing the antenna, you are feeding the antenna like this, because we are not feeding the antenna at the end, but we are feeding the antenna with some offset. That is mean by we are having an inset feeding. So the calculation of the input impedance is very important to know at which position we have to feed the antenna. So let's see what is the importance. We have seen earlier that these are like the open slots where the radiation happening. So as these are like the open slots, the impedance at these positions will be very high. So these positions will be having the very high impedance. But if we want to connect this antenna to any coaxial cable or anything, we know that coaxial cable having impedance of 50 ohm. So we have to find the position where the impedance is matching to the 50 ohm. So as the impedance here is very high, there will be some position inside this patch where the impedance is matching to the 50 ohm. So this input impedance calculation will help us to find that position. So based on the equivalent circuit, these radiating slots can be considered as the parallel combination. So this radiating slot is represented by this parallel combination, and this is represented by this parallel combination of resistance and conductance. So we know that as these dimensions are same, B1 and B2 are same, G1 and G2 are same. So the G1 can be calculated by the expression these thing, and as this both the radiating slots are separated by a distance of lambda by 2, when you add this B1 and B2, it will be cancelled out, because lambda by 2 corresponds to phase shift of 90 degrees, so it will can cause, sorry, 180 degree, and it can cause the cancellation of B1 and B2. So the effective parameters will be corresponding to G1, G2. So the total input admittance can be given by Yin equal to 2G1 plus or minus G12. G12 is the coupling effect. So the input impedance can be given by 1 by Yin, which is equal to 1 by 2G1 plus G2. But the important equation that we have to consider while designing the antenna is this one. So here you can see that Rin, that is the impedance at the position y equal to y0. Maybe I will show with this picture. So this is the dimension showing the inset, that is the distance from the edge of the patch to the feed position. So we have to calculate the y0. So the impedance at y equal to y0 can be given by the expression r in y equal to 0. So this is the position where y equal to 0. R in y equal to 0 to cos square pi by L lambda 0. So it has a cosine distribution with respect to the length and the offset distance. So if you divide r in y equal to y0 by r in y equal to 0, that is plotted here, you can have a cosine distribution with respect to y0 by L. So that is plotted here. So I will explain what is the physical importance of this thing. So we have seen earlier that as this is like an open slots, the impedance will be very high. So that is the impedance at this position will be very high, and at both the ends will be high, very high. So when y0 by L equal to 0.5, that means that y0 by L equal to 0.5 means it is at the mid of the position. So this is the position, and here you can see that impedance at the position will be 0. So if you are going to feed this at this position, the impedance will be 0, and here the impedance is maximum. So if you can find some position in between, there will be some position where the impedance will be having the value of 50 ohm. That is the value we have to find out. So if you want to find out that, we have to know the value here. So maybe I will show while designing how you can find the value of the impedance at this point. So this is just a practical example. If I know the value of the impedance at this position, how can I find these dimension y0? So I know the impedance at the y equal to y0 is 250 ohm. So maybe using the simulation or something, I have calculated the impedance at this position as 250 ohm, and then I can find the position along the length where the impedance become 50 ohm. So here you can see that at around 14.1 the impedance is 50 ohm. So I have to feed the patch at the point of 14.1. So this length is 14.1 to have a better impedance matching. That is the importance of input impedance to find where you have to feed the antenna. Okay. So next, sorry. So next is just a comparison of the patch antenna with the dipole antenna. As we have seen the dipole antenna basics and the simulation, I thought just to make a comparison. So here also, sorry, this is the length, not this one. Sorry. So we know that this length of the patch antenna is also similar to the dipole antenna, which is also equal to half the wavelength. So similar to dipole antenna, these edges are acting as the open. So the when you consider the current, that is this current, you can see that the current will be 0 at these both ends. So the current will be 0 at both ends. And when you consider the voltage as it is the open, the voltage will be maximum at this position. So these are the voltages. Here you can see the voltage will be maximum at this position. And this is showing the half wavelength distribution. When you consider the impedance, impedance will be like this. So we can in effect consider the patch antenna similar to a dipole antenna. But in case of the dipole antenna, we don't have a ground plane like this one, means like a dedicated ground plane. But in case of the patch antenna, this is similar to a dipole antenna with a ground plane. Let's compare the current and voltage distribution on the patch antenna and the dipole antenna. So these are the current distribution. Here you can see that, oh sorry. So here you can see that current is concentrated mainly at the midpoint. Here also you can see that current is concentrated mainly at the midpoint, and at the edges the current is minimum. So this is similar to dipole antenna. So if you consider the electric field, you can see that electric field is happening mainly at the ends and similar to dipole antenna. So the let's consider the radiation pattern. So we have seen that in case of the dipole antennas, it doesn't have any dedicated ground plane. The radiations will be occurring to all the regions. But in case of the patch antenna, as we have the ground plane, the radiation coming towards the ground will be getting reflected back, and we will be having the broadside pattern. So broadside pattern means if the radiation is happening perpendicular to the axis of the antenna. So this is the axis of the antenna and the radiation is happening perpendicular. So we have the broadside pattern for the rectangular patch antennas. So this is the design step for the rectangular patch antenna. First you have to calculate the width, then effective dielectric constant, then extension length, then the actual length, then the inset feed positions. So in our simulation video, let's see how you can utilize these steps. Thank you.